we're meeting Sunday. Yeah, we should meet Sunday. Like make a presentation basically. Like briefly start. We talked about that.
So let's get started. So welcome back. Thanks for everyone who came here despite the nice weather. So I would like to be outside too. So I injured my thumb, so hopefully I'll make it through the writing on the slides. So we'll see how it goes. So before we get started, a couple of kind of things to notice. So let's see, I'll talk a little bit about the final report today, which is due in a week. Okay, also homework, the last homework on graphs has been posted. You should be able to get started on it. Should be able to, I think everything we cover, you'll need for it will be covered by the end of the lecture today. Again, I hope it's not too challenging. You're going to be working with a pretty small data set. I didn't have you do a lot of pre-processing of the data. There's one data set that's going to be M. It's in a CSV file. It's a 10 by 10 matrix. All right, so I picked a small data set because I think it's illustrative to kind of look at it and think through what's going to happen and maybe even see what's going to happen while you're actually running the algorithms, instead of running something much larger, which has other challenges, but then is kind of opaque what's happening. You can definitely run some much larger stuff if you want as well. And then what your homework is basically the main part of it is we talked about 4 algorithms for finding this Q star vector, the limiting state, and I'll start this lecture by talking a little bit more about them again. You're going to implement all of them on this small matrix and kind of evaluate how well they work yourself, and just kind of some analysis, including some pros and cons of these, and then we'll do a little bit of variation based on this, based on the kind of the tweaks you use for PageRank as well. So it should be hopefully not too hard. I know end of the semester is pretty jammed up. You have your projects to work on here and probably other classes as well, right? So try not to end load the homeworks in this course. All right, any questions, concerns about it? If not, it is due the 23rd, but feel free, it will be evaluated. We'll ask you questions about this unit on the end-term test, which will be in less than 2 weeks. So you might want to do it before the end-term test to kind of study for it. I think we may have had mistake of ordering the frequency estimation streaming stuff before the midterm test, and I think many of you would have done better on that section if you had finished the homework first. So I suggest you do that. Okay, I may have to re-ask questions about that on the end term because of that. Yeah, so okay, great. Let me say, before we get into PageRank, okay, a little bit about the final report. Okay, so it's going to be at most 4 pages per student. I had a student in this class before, a project where they decided to make the margins like 1/4 of an inch and use 8-point font. Don't do that, right? I am going to read through all the reports, and I'm going to spend, there's a certain amount of time I'm going to spend every report. Make it easy for me to read. If you write well and leave white space in there, it'll make it easier for me to find stuff. If you use kind of charts and plots and examples and equations, I will get more out of it in the time I'm reading through all the reports. Okay, I'm giving you 4 pages per student. I think it's good to have kind of an upper limit on it and give you a sense of what I expect. All right, you can use space. Okay, so a couple of things that people every year forget. Make sure you have a succinct title and name, okay? And so this title and name, some of you have chosen one already. Some of you use your actual names as the name of your group, but come up with a name for this and make this the same for the poster. Okay, so we want to kind of align the reports in the poster. So come up with a title for your project, okay? Then make sure you describe the problem definition and like the motivation and the data. Probably you've already done that. You've written a project report, a project proposal, you've written kind of a data collection report. Reuse a lot of that. You've already done this, right? And then the main thing I will be looking for, and I want you to highlight, is what is the key idea that your report's about? What is the cool, big thing? I want to see that. I want to see something cool, new idea. I don't want you to say, well, we ran the algorithms from class and here are the results. No, what's the new kind of interesting aspect about it? You know, all of you have that from the intermediate reports, but make sure that's highlighted. And it's clear for me to see that. That will make me interested. I'll probably spend more time reading and kind of thinking about what you actually did. And then the bulk of the report will probably be kind of how did you evaluate what you did? You're going to be thinking about the techniques. So the techniques you use in implementation, comparison, extension, explain what you did in the report. Okay, so I know that you actually did stuff. This should be at least something from class, right? This will be something from class. Okay, most of you had chosen from intermediate reports. There was something to do from the class that was already baked in. You had already done it. That'll be fine. A couple groups did not. Make sure that you ultimately are using techniques from class. This is not a machine learning project, for instance. Okay. And then you will also, I want to see lots of charts, plots, examples, math. I like reading all of these things in the report. It'll make it kind of easier to read. That's part of the 4 pages per student. Okay, it's not just 12 pages of text. Please don't turn a report that looks like that. Make sure it's got some interesting stuff in there. And then finally, I would like to see some discussion at the end of, well, did you think this worked? Okay, and it's okay if you think the answer is no. Okay, it's if you say, you know, we tried all these things and we believe we followed the right techniques, but our hypothesis on what we thought was going to happen turned out not to be true. That's better than claiming it worked when it actually did not work. Okay, if you claim it worked and I disagree with your conclusion, that won't end well. But I'm not going to be too harsh on these, but if you don't think it works, it's okay to say that, or to say what worked and what did not. Okay. Yeah. So I like reading these reports because I learned something from them, a different experience, what worked, what didn't work, what techniques were really useful. This has really helped me shape a lot of what content now is in the class based on making sure I teach things that were actually useful when people actually tried to use them on projects. Okay, so I really appreciate kind of seeing these sort of conclusions in the reports. All right. Yeah, there will be some groups who will have done way more work and done really awesome stuff than the average group in the class. And so I will probably reserve, this is worth 50% of the project. I'll probably reserve full 50 points for these totally amazing groups, which there will be a few of. but so the hitting all these marks and we'll get you an A on the project, but not necessarily all of them. So, okay, so I leave a little room at the top for the really amazing. So if you get, say, more than 45 points, you should be, you've done a really great job on the project. All right, but all right, great. Any questions about project report? Okay, and next class, I'll try and talk a bit more about posters. Oh, one more thing before we get into it. Yeah, so I'm going to do some community detection topic on Monday next week. And then Wednesday next week, I haven't totally decided what I want to talk about. It could be about how to work with graphs on very large scale data, sparsification in graphs, and maybe something new on these so graph embeddings and graph neural networks a bit. Does anyone have any preference? Who wants large scale algorithms for graphs? Who wants sparsification on graphs? Who wants graph embeddings, graph neural networks? Okay. I will try and put together a lecture on that. That's the one I don't have material for yet, but that's okay. Okay, great. Okay, let's get back to this. Okay, so we had talked about, I'm going to start by finishing up the lecture on Markov chains outside of the PageRank kind of setting. And then the PageRank lectures, that's going to be kind of a lecture on how search engines have traditionally worked, right? So we're going to have a Markov chain. Okay, and this is going to have three components, V, P, and Q0. Okay, so V is going to be the set of states. Okay, and if we're working from a graph, then this is going to be the nodes. Nodes V in G equals VE, right? Okay, the second one, P, is going to be the probability transition, so matrix. Okay, we've somehow have determined a way that probabilistically you move from one state to the next state, and we've talked about encoding this inside the matrix. Okay, and then this will be kind of the L1 normalized, the adjacency matrix. Okay, so if we're kind of deriving this from the graph, okay, and then Q0 is going to be the initial state. Okay, and so here we said if ergodic, then not so needed, or it's so arbitrary, meaning that it doesn't matter what we picked as the initial state. Whatever we picked as the initial state would work. It's going to give us, eventually going to give us the same answer. So we're hoping that we're somehow setting this up as going to be ergodic. And then if we do that, then it's not going to matter. Okay, if the graph, so just a preview, we'll talk more about how to make things ergodic today. That's a big component of getting PageRank to work. But if the graph, the vertex edges, is connected and undirected, then if I do L1 normalize of the adjacency matrix, then this will be ergodic. Okay, so because I will be able to walk back and forth on every edge, as long as, and or if this is, I guess, and the number of nodes is greater than 2. Okay, if I have 2 nodes in a graph, I just walk back and forth between those 2 states of the graph. Okay, but if I have more than 2 states and that graph is connected, and I can walk back and forth in every node, that's a cycle of size 2. And I have an adjacent cycle of size 2. I can mix them up and I can get anywhere in any number of steps. So basically, if I start with an undirected graph and I do the L1 normalization procedure, then I can guarantee it's going to be, and this is why I talked about this procedure, I can guarantee it's going to be ergodic, and then I do not need to care about this initial state. Okay, so if I have a connected graph, then the set of vertices is from the graph, the transition matrix is from the adjacency matrix, and I'm basically analyzing some properties of this graph. Okay. Okay, so then, all right. So then we talked about, we wanted to get this state, this limiting state Q star, which was basically so for I equals 1 to kind of infinity of Q get the probability transition matrix times some state Q, right? We think of it like this for loop. And so we could think of this as an algorithm and this Q star. So Q star equals the answer in the limit. And this is unique if so ergodic. Okay, if it's is it unique? I think it's almost always unique up to there might be some weird cases based on ties and eigenvalues, but I think it's probably unique if it's ergodic. Okay, so and the question was how do we compute this? What's the right way to compute it? So algo for Q star. Sorry, my handwriting with this brace, my thumb is not great today. Okay, so the first one was Q star equals, so I do the eigen decomposition of P. This gives me V times lambda, okay? And V1 equals the top eigenvector. And then Q star is going to be V1 divided by the L1 norm of V1, okay? 2 is going to be Q star equals P n times Q0 for large n, right? And so I'm going to pre-compute P to the n equals P times P times P, and I gave you this trick that maybe I can break it down into these powers of 2. Okay. The third way is Q star equals kind of this for loop I equals 1 to n of Q equals P times Q, right? Where I just update this over and over again. This is equivalent to the power method. Okay, remember for computing eigenvalues, actually this is one way of computing the eigenvalues, is the power method. And then the fourth way, which we'll talk a little bit more about, is do a random walk and keep stats. Okay, and there's a couple of things. This is to keep statistics on how many times I visit each node. There's a few tricks you need to make sure to get this to work. If you start at Q0, you're going to deterministically keep Q0 in the state space, right? And so then the next step is going to have to be a neighbor of Q0. So it's not completely unbiased estimate. It really, this random walk will kind of depend on where you start if you just keep statistics. So you have to start with a, so burn in period of say 1,000 steps. Okay, so typically before you keep statistics, you walk 1,000 steps until you're, or some number of steps until you feel you're at a random location. And then you can keep statistics. Okay, when this is formally analyzed, and there's been kind of a lot of theory written on this, that you should not actually take every single step. You should actually take some number, let's say 100 steps, and then keep one statistic. Then take another 100 steps, like a mini burn-in period, and take another statistic. Okay. So in theory, you're supposed to do that. In practice, that if you're collecting a whole bunch of these things, you don't really need to do that. Now, your estimates of how fast this converges are not going to be kind of the rate at every step. So, okay, so the point is, in order for you to get this work, you need to take a huge number of steps. Okay, something like after the burn-in period, to start getting any sort of useful estimates in anything, I would say at least 500 steps, at least 5,000 steps, and maybe much more. So at least 500 or 5,000 steps, I would say, is what I have seen used in practice in these things. Whereas these values of n, these converge at the same rate here because they're really kind of analyzing this same sort of convergence. I'm just doing the computation a different way. So this number of n, I would say this is maybe n equals to maybe 20. Okay, so maybe you only have to do 20 steps here. Now it's going to depend on the matrix in the system. It might be less than 20. It might be more than 20 that you have to do here. And it may depend on where you start. Where's your Q0? So these require many fewer steps. Like if you want to make it a power of 2, maybe you go up to 16 or 32 steps with that thing there. So which one of these do you think that is most commonly used? We had a vote at the end of lecture last time. Did anyone think about it and change their mind, or is more confident, or look this up a little bit? What do you think is most commonly used? Yep.
Let's say it's the eigen decomposition, because it just seems like that's the most straightforward computation that one could do.
Yeah, okay, great. So everyone agree with that? Eigen decomposition is the best way to go. I will say that it's sometimes the best way to go. Okay, will give you the most precision, and in fact, most of the eigen decomposition code that you would use, you would not write yourself, and it's been really well optimized. So on matrices that can fit in the memory of your computer, and if you get it into MATLAB, it's going to be hard to beat that. Okay, if you're starting from an arbitrary state, you don't know what a good state to start is, then this is probably a pretty good thing to do. In fact, you can call a version of the eigen decomposition in your code. It varies whether you're using MATLAB or Python, whatever, but you can say, I don't care about the whole eigen decomposition. When you get the whole eigen decomposition, I get the V and lambda, which is V is going to be an n by n matrix. I may not want to report that. Maybe I only care about the top one vector here, which is what you care about here. You can run code that will just find the top vector. Okay, and that's been quite well optimized, and it will run that for you, and will work quite well. Okay, the secret for what it will do to compute that is it actually uses number 3 to compute that. Okay, oftentimes. Okay, so number 3 is what it actually does to compute it. It picks a random queue to initialize. Okay, and then it turns out, I once asked this open question, I don't think it's totally resolved. I think you don't know how to do it without a random queue to initialize to guarantee it actually works. Okay, but it pick a random queue to initialize and then run this like power method. And it will probably have an internal way to check whether it's converged or not. It doesn't know how many steps. It maybe will run steps until it seems to be kind of pretty stable. So this is called the power method for finding the top eigenvector, and it's a quite effective algorithm. All right, or there's some versions of it that do a little bit better for higher rank. There's versions of it where you keep around some extra bases and then you reproduce it afterwards. But it will run something very close to what the power method is. All right. Okay, but there are reasons why you would not want to actually call your linear algebra package 1. What would that possibly be? Why would you not want to do 1? And you not want to do it and say, well, if it was correct to invoke number 3 exactly, then invoke that with a random Q0, but maybe do something else depending on the scale of things. What would be a reason to do one of the other approaches? Okay, so even if you did the power method, it's going to call it with the random Q0 to initialize. Okay, but what if you already had a pretty good guess of what the state was, or what the stabilizing state was? If you started with that, that might work better. It'll converge faster. It's kind of converging towards the right answer. And if you start near the right answer, you won't have to take as many steps. Okay, yep.
Because if you already know your Q0 or have a good idea that initial state to best guess to be good, because the only thing you need to do is just the event, which at that point is just, matrix multiplication.
Yeah, so yeah, okay, what's the difference? Yeah, so good. Let's say I could pre-compute P20, P to the power 20. Then I just do 1 matrix multiplication. What would probably be the difference between 3 and 2? Let's say I know I'm going to run this a bunch of times, so I pre-compute P to the 20. Why is this maybe not a great idea to? Thinking about from graphs, right? Let's say we got this from a graph. It's going to have let's say it has 100,000 nodes and 1,000,000 edges. Okay. Yep.
Well, with number 3, if we're choosing a random queue with 100,000 nodes, probabilities of us picking one that's not the biggest one.
Yeah, so if we had pre-computed P20 and we had an initial guess, it's going to give us the same answer as this one if we ran this 120 iterations, but it will do with 1 linear algebra computation. So it'll give us the same answer. So a good guess will help, and it will converge even more precisely, right? Than if we had run this for 20 and said, that's close enough. Maybe I get 3 digits of precision with 20 iterations, but if I had a good guess, and I ran 20 iterations, then I can maybe get to 6 digits of precision, right? So I can get more information if I run this more, okay? But if I have 100,000 nodes, right, and I have 1,000,000 edges, so how many edges does every node have on average then? So actually, so 20, because every edge touches 2 nodes, but okay, about 10 or 20, right? So that's much less than if every edge had close to 100,000 nodes, right? 100,000 edges, right? If it was a dense graph, it'd be 100,000 edges. Well, so what's going to happen is that if I multiply p to the power 20, it's going to go from a very sparse matrix where I can just store where the edges are to a very dense matrix where I have to store 100,000 times 100,000 edges, basically. Okay, so people typically do not use number two. It seems really cool. I pre-compute everything, but you're pre-computing and storing a very dense matrix, p to the n, and the probably transition matrices are usually very sparse, which means that this step I can do very fast. I only have to look at the edges that actually matter and update on those edges. And so if I'm clever about how I implement this with sparse edges, I can do this one three much faster than two. Okay, and much less space efficient. The graph I described might fit easily in memory before, but after p to the 20, after it becomes dense, it may have trouble fitting in memory. Or there's some scale where this will fit in memory and number two will not fit in memory, and then you have to worry about thrashing and bottleneck issues. Okay, so number two is not used too often. Okay, number four is still actually used. Okay, it seems super slow, right? I have to do at least 5,000 steps here, but every step should be fairly fast. Do this burn-in period, but okay, let's not worry about that too much. But this one is in some sense more powerful. The first three rely on linear algebra, which means that P needs to be written down as a matrix. Okay, this one does not actually require to be written down as a matrix. I just need a function that I go from one state and what's the probability I go to any of the neighboring states. So it's much more general and it can handle continuous state spaces. Okay, and so this has made it very powerful and have a whole bunch of other contexts. In Bayesian analysis, where you're trying to compute the probability of certain kind of the distribution of possible outcomes, they often try and write down some formulation and then sample from the thing relative to the likelihood of it using this formula. All right. So it is much slower, but it's more powerful now. Yeah. Okay. So I want to talk about this second way of thinking about these Markov chain methods and give a little bit of context before I move on to PageRank about this Metropolis algorithm. So this came out of 1953. These people, I think, mostly or all of them worked on the nuclear bomb at like Los Alamos. Probably, I think, forget if they were in like the Oppenheimer movie or not, but they're two husband and wife teams, in fact, with the Rosenbluths and the Tellers. And Metropolis had the coolest name, so the algorithm got named after him. This is an algorithm that was very influential, and it was basically developed to try and understand the physics of the nuclear bomb going off. And they're trying to understand kind of a state space. So they're saying that there was going to be some sort of so I could write down a kind of a state Q. This is of the so physics, right? There's some physics that I'm modeling, and Q described the state. Okay. And what was key about the state was the energy. This is the energy. Okay. And if I describe a state of physics, it tends to move in directions with a lower amount of energy. Okay. It tends to settle. If there's a fire, it burns out the fire and the energy is used up, right? If I have a marble on a hill, it will tend to roll down the hill to a lower state. And this is true of lots of physics, including complicated physics like from the nuclear bomb. Okay, and so I will now kind of, so there's some kind of state space X, and so Q is going to live in X, and I want to kind of do a random walk of Q in X so that the probability Q is in state, let's call this X, is proportional to the is proportional to the I'm not going to get this right. It's something like it's proportional to this weight of Q, which is going to be e to the negative the energy of Q. Okay, so there's going to be some. I want the probability it's in a particular state to be proportional to this weight, which is e to the negative the energy of the state. Okay, so if the energy is really high, it's very unlikely to be in that state. If the energy is low, it's more likely to be in it. And so I want to kind of think of the physics as kind of simulating this. It kind of is stochastic and how stuff moves around. Particles might bump into each other and they might cause something to go into a very high energy state, but generally then it will kind of dissipate into a lower energy sort of configuration. And they kind of want to model this property to understand the state space of where reactions could possibly go. Okay, and so this way of defining this weight could be written down as a function of computing the energy, right? So I can compute this one term, this described by some physical equations, and given the parameter system, I compute some score, which is the energy, and I can turn this into a weight. Okay, so I need this one component. And then they came up with this algorithm, which is kind of in the mold of kind of the fourth paradigm we talked about. You initialize at a particular state, V0. You can think of it as a kind of a finite state space, but it really could be infinite. And you repeat, and you do kind of, there's this, how you describe the probability transition here is kind of in two steps. First, you generate some neighborhood. This is the neighborhood of V. And this is described by, think of it like a Gaussian kernel. Describe a probabilistic description of what is the neighborhood of V, something nearby to it in the state space. And then you do a check. If the energy is of U is greater, or if the weight is greater than before, so the energy is decreased, I always take that step. Okay, so if energy decreases, always take the step. Okay. But that's not always true. If not, if the energy increases, right, then I get to the else statement, the energy is increased. Because I'm in this state here, the energy has increased. Well, then the new state has, this is always less than or equal to 1. Okay, so then if the energy has increased, I still sometimes do that. But the more that the weight has decreased, the less likely I am to do it. Okay, so I'd rather be in a situation with higher weight. But if I find that I'm in a state with a higher weight, I might take it proportional to the ratio of the weights. Okay, and so it's important. It's the ratio that means I don't need to actually worry about normalizing the energy. And so then, if I don't do this, then I stay where I am. Then I stay, right? The last. So if all the neighboring locations are always increasing the energy, I might just stay put. Okay. So then, and that may indicate that maybe I need to shrink the size of the neighborhood to actually get the Markov chain to actually move around. Okay. And I do this until it's converged. And how do I know if it's converged? This is kind of much longer story. Oftentimes you don't. but then you return these states and you take the statistics on the distribution for this. And this is guaranteed in the limit to be sampled from the distribution W. And from there, you can infer something about the distribution of the energy. Okay, and so this is a really powerful tool, and variations on this is how you do this Bayesian analysis on continuous state spaces. Okay, and this is also Markov chains, but this is not really modeling graphs, but this is an analog to continuous settings instead of these graph settings. All right, any questions on this? We'll move on to PageRank. Go back to big scale linear algebra in the web. Okay, cool. So, okay, so PageRank. So PageRank is really a story about web similarity search. Okay, so who before this I started talking about, who's heard of the PageRank algorithm before? Okay, about a third of you. When I first started teaching this course, this was all the rage, right? This was kind of a big deal, like deep learning is or generative AI is now. PageRank was the cool algorithm everyone was using, and it was kind of the foundation of why Google was able to kind of take over the search, like the search market for the web. And they had this cool insight, this PageRank algorithm that allowed them to really identify important web pages and promote those in the search. Okay, so before we start into search, let me comment on, is search as a web search, so in ranking objects, let me describe the basics of how this works. So how you actually serve a search query is you build an inverted index, mostly ahead of time. Okay, Google serves, queries all the time. I don't know how many they do a second. It's incredibly rapid, and they don't pre-compute. They don't run LSH or something every time you ask a query. They pre-compute these things. If I have the word apple, right, then it's going to pre-compute kind of a ranked list of pages. Page 1, page 2, ... right? And probably it maybe only needs to store up to page 10. If you look at the first page of Google search engine, there are only about 10 things which are shown, and then you can click more to see more, but the time you did to click more, it can run stuff in the background. So it needs to really pre-compute the first 10, and maybe there's also some meta information or something else going on. And there's kind of a bunch of words, kind of bank, and it also has the page 1, page 2, and car, and it's pre-computed this for a bunch of queries. Okay, this seems odd. You can type anything you want into the search box, but typically people don't, right? There aren't too many things that people type in the search box. Almost everything, the first 100,000 searches, is not that many from the scale of Google, and they've pre-computed answers for all of the first roughly 100,000 searches. I remember when I was like 20 years ago, I saw a talk from someone at Google, and they had just kind of launched some of this. So keep in mind, 20 years ago, I think the first 5 most popular searches were variations on the spelling of Britney Spears, right? So they were all Britney Spears, but they're all spelled in different ways. So this was 20 years ago. Now it's, I don't know if it's probably something to do with Trump or something as the most kind of the avatar of the web, or Taylor Swift. But like those names are maybe easier to spell. But there are not like, it really gives you a sense of people typically don't search too many different things on the web. And they pre-computed all of these things. Okay, and so it can quickly serve these. But now the challenge is, how do you pre-compute this? How to pre-compute? Oh, and then you might ask, you search Apple and bank in the same query. Well, basically, typically what it does is it looks at the two ranked lists and somehow merges them to find web pages that have to do with apples and bank. And if enough people search Apple and bank together, they may do a whole search just for the combination of keywords. Okay, so with 100,000 things pre-computed, they can actually infer things by taking this short list and merging them together to find the best rank. And I'll do that very quickly. Okay, so question is, how do we define this pre-computed ordered list of things, the most relevant pages for a particular topic? Okay, and before I talk about this, I just want to pause and say, is search kind of dead? Is AI now kind of these chatbots replacing search? There are definitely some, like, so Google, where 90+% of their revenue is basically coming from ads displayed on search, are very concerned that this could be the case. So investing a lot in AI, the kind of generative AI. In some sense, the information is stored within these large neural networks and they're just kind of querying it. But that's not entirely true. There's this method called retrieval augmented generation, which basically runs a search query in the background, finds the pages that are most likely to be used to answer the question, and then puts those in the context of the question asked to the chatbot. And the chatbots kind of, maybe with some pruning, with some more careful stuff, puts them in the context. And then the chatbot will use those as part of the question to produce usually better answers. Right, so it's still using some search as some component of this. And this RAG is kind of a very powerful method in this context. Still not totally clear, but I don't believe this indexing and searching is totally going away. Okay, that's my thought on it. And I'm not 100% sure, but there's some stuff might be replaced by this. Okay, so let's ask this question now. How to pre-compute this list of pages, right? How do we compute this order? Okay, and in the context of Google, these are web pages. In the context of like Amazon, they have the search engine over their products, which is not quite as big as the web, but pretty big. They have their list of products somehow that they're displaying to, but there's a bunch of text associated with the products, right? And this has, so say page 1, is going to have a bunch of information in it, okay? And it's going to have some kind of title, and there's a bunch of other kind of meta information on the page. Okay, what else is possibly useful on the page that would be useful for a search query? The main thing that had been that there's a bunch of text, right? There's some text on this page. Most of the content used for building search engines, at least traditionally, and we're going to go back in time a little bit, pre-Google, which I don't know, maybe that's before many of you were born. So pre-Google, they basically were just looking at the text on the page and maybe a little bit about the title and the meta information, right? You can, if you ever write HTML, you can encode some keywords inside the meta information, and this may this may help as well. Okay, and so I somehow want to turn this into a query. Which web pages are most so relevant? How do I determine this? Okay, this is kind of something we've already looked at in class, and there were kind of two predominant methods. There was the Jacquard on the K-grams, okay, and then there was the cosine on the bag of words. Right, so the Jacquard K-grams, we represent everything as a set. The cosine is a bag of words. We represent everything as a high-dimensional vector, right? And then we looked at the cosine similarity between them. And then they pre-computed these lists by computing something like using min-hashing or locality-sensitive hashing, right? Min-hashing was developed for Jacquard similarity. Cosine was developed, or locality sensitive hashing with the kind of for cosine similarity was developed for this context. And these two technologies came out of this particular application. Okay, and you could think of, well, the title and the meta information might be weighted a little bit more than just the text, but basically you threw it all into some sort of representation, and then you could do a Jacquard or cosine similarity to do, you know, and then you would pre-compute with the min hashing or with kind of locality sensitive hashing, right? Specifically with the cosine version. Yeah, yes, okay. So this was how the first search engines actually worked, right? There were like Alta Vista. Okay, so right, well, today Alta Vista was an early search engine that basically worked by trying to catalog all the web pages it could find, and then would pre-compute an inverted index for Jacquard or cosine similarity for a bunch of useful keywords. And then if it was outside the scope of the ones it had indexed, then it would try and run this on the fly. Okay, so this was basically how it worked. Okay, why is this not just what we use today? What do you think happened when these search engines became popular ways to browse the web? Free search engines. What happened? There were these like Usenet groups, and there were people who you could find something by navigating through the web by one page to the other, or someone, you know, set up something and you knew the address and you would go directly to it. But you kind of had to know where to go. It was kind of like going in a taxi. You give them the address, you close your eyes, and you wake up and you're at the site. It actually may not have been much slower than actually taking a taxi ride in some places. Okay. Okay. So what was and a bunch of things, these search engines became popular, and then this kind of this method alone did not work sufficiently for what it was supposed to do. What do you think was the first thing that broke when just using this one? Yeah, so yeah, go ahead.
I see that these methods are primarily relying on text, so I'm gonna guess that once web pages start to be embedded with more multimedia things like photos, videos, that sort of stuff, it's kind of hard to run Jacquard similarity or whatnot.
Yeah, okay, this happened much later than what I'm talking about. There were images, but it would take 30 seconds to download a single JPEG. It was so that at this stage we did not know how to do any sort of search on sort of images. That's way in the future here. Yeah.
Maybe some people just like
yeah. So this is what I want to hit on. These fake web pages. This is before we really knew how to monetize the web. Maybe eventually ads really monetize the web, but people wanted to have web pages lots of people went to. Maybe there was this, I mean, remember what the scams were back then, but it was, but there were these fake web pages, and what they would do is if it was, so that they would try and create a web page that maybe just copied all the text, right? So what they could do is you could run like Alta Vista with the word Apple, and you go and you find page 1, page 2, okay, and now you create your web page, okay, and you put the kind of your stuff up top that everyone sees. And then down here, you copy all the words from page 1, and then you copy all the words from page 2, and so on. So you can copy them into the bottom of your web page, and maybe kind of people could, maybe they wouldn't scroll down to them. It wouldn't. Or you put them in white text on like a white background and no one can actually see it, right? Or you just take the word, let's say instead, I can take the word apple. I know that's the search. I just copy the word apple over and over and over again in the bottom in white text, right? So, okay, the cosine similarity is going to be super high because the bag of words count is going to count how many times apple appeared. Well, it appeared 1,000 times on this page and only 100 times on your page. So it's going to direct to my page, right? So it's going to win the kind of this automated method of doing it. And so kind of this, the Jacquard base, which is counting sets, was a little bit more robust to this because it had to have the context, but you could still fool it by copying whole pages that scored well. And if page 1 and page 2 both scored well, why not put both of them in? And that will cover more categories. Okay, and so you could put these fake web pages to really gunk up stuff on the web, and then you could add maybe your ads onto this web page. Okay, and this has kind of been a problem that has plagued search engines for a long time. Right. Yeah, so the big innovation from, and there was a bunch of evolution on this where they tried to tweak their engine and figure out how to identify these pages and so forth, but it was this back and forth the same way like spam is in your inbox. Okay, and then Google had this kind of this cool idea of PageRank, but it was predicated based on how did these web pages actually know which web pages to put in their index. Okay, and what they use, which is still used today, was called like a crawler. Okay, a crawler is a program that surfs the web. Okay, it's kind of one will visit a page, it will record kind of info on page. It will check it against the keywords and kind of put in the index. So it used to be if you update your web page, it might take a few days before Google's crawler would search the web and find it again and update it in the index for new information. So, but they were running these programs that would do this and find these and put them on inside their index. But how would it find new pages? Well, then it would go to random linked web page. Okay, so go to a randomly linked linked web page from the page it's currently visiting. Okay, so then it would find new web pages by just exploring links, and it would be able to crawl around the web from one node to the next. Think of the web as like a graph, and it's kind of a spider crawling on this web graph. Okay, and this was the intuition and where a lot of the name convention had been coming from. Okay, and so it's going to do this and it visits a new web page, it indexes. What could possibly go wrong with this? If I just send out a crawler, and they're running thousands of these crawlers, millions of them at once, right, to try and get to the web. But if I go to a web page, and step 3, to find the next web page to go and report, I have to go to a randomly linked web page. Well, yep.
What happens if there are
Yeah, great. So what if no linked web pages? And so with some probability, or if I'm at or I'm at a dead end where there are no links, and usually this was like 15%. Okay, I go to random page. Okay, and it goes to a random page. Remember, it has this huge index of all these pages it stores. It picks one of them at random and it goes to that one, and then it starts walking again. Okay, so if it about every 15% of the time it does this anyways, that means it makes about 7 steps from a random page, and then it follows them around, and then it jumps to a new page. Or if it gets stuck, it will, it gets into a dead end. It will jump to a random page. And this is how the crawlers work. This is how they found the web pages that they put into their index, right? So this was already working, okay? So what does this remind you of from our earlier part of the lecture? It's exactly a random walk, aside from this what happens in the dead ends and the 50%, right? It's exactly doing a random walk. This is the 4th version, where it's randomly walking one state at a time, and they could just keep the kind of statistics on which web pages were more likely to be hit. Okay? And if you have this 15% chance, or if you have a dead end, you go to a random web page, well, it's going to be fully connected. It's going to be organic of all the web pages they've indexed so far. If there's part of the web that's not connected to anything else, sometimes from direct links or from other links, this is sometimes called the dark web, then it can't index as part of the dark web. Okay, but of all the non-dark web, it can it can build an index on here. This becomes organic if you make sure you have this step in here. And when I first learned about this, I thought 15% was a pretty high number. That seems if you really want to model the random walk on the web, that seems pretty high. I'm like, that can't really be true, but it's pretty close to this what they use. And this, I think they tried things and they came to this number because it worked pretty well for a variety of reasons. We'll see. We'll talk about at least one of those reasons. Okay, so this was building a kind of this was keeping. So the first idea was you could just keep statistics of which web pages you're likely to find in inside a random walk. Okay, but these crawlers were used. Before I talk about exactly PageRank, let me go back into another history lesson. Kind of alternatives to search engines. Okay, so it was not clear before Google came on the scene. There was Alta Vista. There was so there was Lycos, right? So pre-Google, there were kind of Alta Vista. There was Lycos. These were search engines, right, that were building this index that you could put in the keyword search. But there was an alternate version, which was just a built like a built index. This is kind of like a Rolodex or something. Rolodex is probably even older analogy. Who knows what a Rolodex is? Okay. So probably I'm like an old time detective novel or something. But it's just like a catalog. It's like the Yellow Pages or something. These outdated concepts. Just trying to build a web page that had a list of links to all the interesting pages. Okay. So this was a web page with lists of links. Okay, and these were organized, right? And these were sort of organized, and so they were trying to automate this still through crawlers. So they were still using crawlers, trying to automate these, maybe help kind of determine a useful ordering to help find them. But it wasn't a search based. It was, well, we're going to organize this, and you're going to kind of look at it and find the section that's about sports or stock market, and you find all the web pages that link to things that they thought were unreliable, and then they could sell placement on this board. So that's how they were making money. What were the big companies that were working in this space? remember, I'm sure there's at least one that everyone's heard of. One, there were two big ones. One was called Look Smart, which turns out you have to do more than look smart. And then the other one was Yahoo. Okay, who's not heard of Yahoo? Okay, everyone's heard of Yahoo, right? They still survive in a lot of other things. They've managed to diversify somewhat before this went out of business. But Yahoo was this huge, immense company built on this kind of organized index with a bunch of links to different things. Okay, there was a lot of people who thought, and for a while, this worked better because it worked better than the search engines. They didn't work all that well, and people thought this is the way forward. It's like a Yellow Pages for the web or something. And so these were huge companies that turned out their method did not stick around. And so Google is afraid that kind of chatbot AI is going to replace whatever their search engine now. The way that these companies are no longer, LookSmart probably doesn't exist, and Yahoo is, I mean, it's been bought and sold a bunch of times, but the name sticks around. Okay. So it was not clear even that the search engines were going to work because they weren't necessarily better than just someone hand organizing the entire web. I mean, more than one person, but it was a huge company. Okay. Yeah, I remember I interned at Yahoo one summer. It was like after Google had come out, and man, it was the mood inside there. They had a cool data mining research team, but the mood inside the company was kind of grim. They kept like, why is Google making so much more money than us? Was what everyone talked about at lunch. It was, yeah. So, okay, so PageRank. How does PageRank work? Okay, and it's basically built on this idea. The idea was that kind of interesting web pages are linked to by other interesting web pages. Okay, so that if you have an interesting web page, probably other pages are linking to it, in particular interesting ones. Okay, that there's some network of more trusted, more valuable web pages, and they kind of self-organize by linking to each other, including Yahoo and these other places. They were trying to link to these interesting other web pages, but there are other more smaller sites. Someone could make a web page. Here's all the interesting links to about fan pages for Cheers, the like the television show. There were web pages like this back then, and that was kind of an authority on that, and it linked to all the other interesting web pages on Cheers, right? And those web pages probably linked back to it, right? So there were these. This was kind of a way to understand this, and kind of the insight is this was correlated with what a random surfer would do. When the web was first coming up and you could click on a web page and learn information, and click on another one and just read and learn about stuff that wasn't available to you before, very cool time. There were lots of random surfers. If you would stay up late and just surfing the web, clicking on web pages, it's like reading Wikipedia nowadays. And this is what kind of a random surfer would do. And they captured that with what the crawlers would do. Okay, and so this is what the crawlers were doing already. So the crawlers already had this information, and they found that the crawlers kept coming back to the more interesting web pages over and over again, more likely than the web pages that weren't that interesting. Okay, so they wanted to build this into the search engine. And so the idea was that they would have a ranking with a kind of something like, it involves something like the cosine of Apple, plus it also depended on the kind of the random surfer. So, so the frequency of the random surfer. Okay, so it really, that the ranking should depend on both the keywords and all the other engineering that went into this to try and fool the spammers. So a bunch of stuff is hidden in here, plus the probability a random surfer would go there, right? So if someone just copied a page, but no one was linking to it, then you shouldn't, then the random surfer would not find it. So this allowed them to distinguish between these spam web pages, the fake ones, and the ones that were actually authorities and that were updated and that were trustworthy and other people linked. Okay, if everyone linked to the wrong information, they would still get kind of, it would get indexed well. But for the most part, people self-organize so pretty well on here. Okay, and that ultimately they realized that this was actually the limiting state. So this random surfer probability was the same thing. They had kind of, as if you were randomly walking on the web, this was modeled by a Markov chain. They could model this as a very large linear algebra problem, and they could solve for Q star. Okay, and they could solve for this using, their data was too big to run. They were famously running this out of like their dorm room and then out of a garage. So they didn't have a lot of computers to run this on, but they could run a version of the power method because it was a very sparse graph. And they could do this in a distributed way. And then a lot of the modern large-scale parallel computing came out of MapReduce by building how to do this on distributed cheap hardware. Okay, so this led to a lot of cool things, running the power method, the third version of the algorithm, to approximate Q star. And so this would update. The crawlers would keep running, and they would need to kind of, So in order to compute this, so to compute Q star on the web graph. So instead of, now they were able to learn the web graph because their crawlers would go and read a web page and see all the outgoing edges. They would have the URL, which uniquely indexed it to another one of these web pages. So the crawlers were now learning the web graph in addition to indexing it. So the crawlers were learning the web graph. Okay, so by looking at the outgoing links, so the set V, the nodes, were the pages, and the P was the outgoing links. Okay, how they actually put the probability, they could just evenly divide it to any link, but they might do something more sophisticated. Links in more prominent locations might be more important. And Google did not quite reveal exactly how they did this. Okay, and so the goal was then to kind of rank page I higher if Q star, if I look at the value, the ith index into this vector is higher. Okay, and so instead of, you couldn't run this on the eigendecomposition, and the page, and this was always, this was updating kind of all the time. So what they would do is each at night, they would run Q star old is equal to their updated so they would update the P, this probably transition matrix, with new links and new things they learned. But they would start with the old Q star that they had yesterday, and they would take all night to run this, right? And they would maybe do one, or maybe they got it up to a few steps overnight while there wasn't too much actual search traffic they had to use the computers for, and this would update. So because they had yesterday's Q star vector, the update was pretty small. So they don't have to do, it didn't change too much by doing one night. And if there was a big change, well, after a few days, it would update. Okay, so this was basically how they computed this Q star vector instead of trying to pre-compute P to the N. Well, they didn't want to do that because they kept updating it, and it took a long time to do. They only had to do one step, and it was very sparse. Most web pages have 10 to 20 links. They probably have more now, but they didn't have too many links, so this would be fast to run one step. Yeah.
But all links on a web page.
That's the default way that is often described. Probably Google had a better system for doing this. They probably eventually identified where certain links placed more prominently are going to be receive a higher probability than other links. But at a first approximation, they just take a look at all the links on the web page and weight all of them equally. Okay, it could be if it's in the header or the footer of the web page, that's treated differently than if it's in the main body. There are lots of heuristics that could be played here, and I don't know exactly how they optimized it. Okay. Yeah.
So at the end of this, what is Q star actually represented in every single like?
Q star is if there are n web pages, it's an n-dimensional vector, right? And it's the probability of a random surfer being on that web page, given that every roughly 7 steps, they jump to a random web page. Okay. Or if they reach a dead end, they jump to a random web page. Okay. Great. Okay. So this is kind of a cartoon picture of the web. The links on the web page, the point is there's some big strongly connected component. This is maybe, at the time I first made this figure, maybe this is 90% of the web, but it's not simply connected from the directed graph. There are some out nodes that don't link anywhere else. So you really need this teleportation step. Often this 15% is called like a, like a teleportation. So teleportation to kind of a random node. This is maybe, think of 15%. So okay. So what's happening is P itself is going to be, so this teleportation at 15% is important because it's going to make this ergodic. If you don't do this, it's not going to be ergodic. You could get stuck in these dead end parts of the web. Someone could set up get some links on some web page to go to their part of the web, and then the crawlers would just get stuck in there, right? So you really need to have this in here. And so the key thing is you can write P as equal to this web adjacency matrix. So maybe this is the link matrix, 1 minus beta, plus this beta times Q, where Q equals the all ones matrix. All ones divided by 1 over n. Okay, so Q is going to be, so I can write this as a single linear algebra operation where beta fraction, this is beta will be 0.15. So this beta fraction of the time, I go to a random thing and I can write this as a single linear algebra. Now this matrix P here, so this is from the web graph. Okay, the web graph is very sparse. But Q is very simple, but it's dense. So that makes P completely dense. So I don't want to run linear algebra on P, which is dense. This is sparse. But I can run this step. I can run this one step in a sparse efficient. Because I just flip a coin, and if I flip a coin 50% of the time it goes to Q, well, I pick a random page. I don't implement that with linear algebra. but I do implement the L part with linear algebra or sparse linear algebra. Okay, so I really want to kind of think of carefully how you implement this, and the random things allows me to do that. Okay, I want to 2 minutes left. Let me talk about a couple things. This didn't end spam farms. You could set up these structures like this, where there's a densely connected part, right? This is like the main web, okay? And then they have spam farms here where they want to promote. They want to promote these web pages. Why is it structured like this? Well, they send links into these web pages, which then feed into here. They have basically 7 steps to do this. So they use maybe 2, maybe they'll have another layer of 3 steps to get to these web pages they want to promote. And then it will get stuck here, and maybe they link back and forth between these web pages. How do they get these gray edges here? These gray edges are like the links in like the comment section, right? Have you ever seen these random links in comment sections to a web page that doesn't make sense? That's what these web pages are. And then these they can sell to people who want to promote their web page, to say, we have these pages that are getting a lot of traffic from things that will get indexed in PageRank, and we can send their links to your web page and promote them. And this will increase the PageRank score of this. So Google has to try and find these patterns in the web and exclude these from the crawlers and the search engine. They need to look for this sort of structure. And so they've kind of gone better at that. And then let me mention one last thing, is that when I do this, sometimes I don't want to jump to a random web page queue. It includes all the spam web pages and a lot of stuff no one links to, but there's kind of a trust rank, or where this is queue is non-uniform. I will start at pages which are more trustworthy in some way. At some point, maybe this was government web pages or university web pages are more trustworthy than other ones. So I would start at those, or at Yahoo, which had all these interesting links, the ones if I trusted Yahoo, instead of a random web page. And this maybe was a little bit better. But then the question was, which web pages should we actually trust? And this, Google has some web pages they trust more, but it's not clear how to actually do this properly. And this has kind of been a big question of how to optimize these things. And there's a bunch behind the hood that is not fully, don't fully explain, because they don't want other web search engines to kind of copy how they're doing this. Okay, well, we'll stop here, and I can, more questions, I can take them off.